Okay, so last time we got into really starting to talk about the atom. Uh, Reminder that there was a number of important sort of experiments that led to the understanding of the atom. The early model of the atom was one put forth by Thomson, which was the plum pudding model, where the positive charge was spread out all through the atom. Embedded inside the atom, there were negatively charged electrons. This was sort of the accepted model for a while until really a big experiment done by Rutherford, who did the gold foil experiment, which basically what he found was when he shot alpha particles, which were these radioactive positively charged particles, at an atom, which he anticipated it sort of being this type of atom. He expected that the positively charged particles would go through all that positive charge in the atom, and there would be a little bit of some deflection that would occur because things with the same charge like to repel each other, get away from each other, while things with the same charge want to be attracted to each other. And when he did his experiment, he was really surprised that for the most part, most of the alpha particles had no problem, basically sailed kind of right through and didn't really hit anything. But he did find every so often there would be these alpha particles that get scattered at these really large angles. And what they had to do was essentially move away from this early model of the atom and go, it is not so correct, to this idea of really the current model of the atom, which is we have this really dense core in the atom, which is the nucleus. Inside there is where we find protons and we find neutrons, protons being positively charged, which is why it accounted for those alpha particles being bounced off at really large angles, because it's a very dense core of positive charge. And you shoot something positive at it, it's going to basically bounce off at a lot of angles. Later on in the 30s, neutrons were discovered, which have no charge. And out in this sort of empty space, if you will, from the nucleus, that is where we have our electrons that are, again, really randomly sort of traveling about the nucleus. They don't travel in pretty circles or anything like that. They travel in a very chaotic fashion. And what is referred to as the Heisenberg uncertainty principle basically says that the more that you know how something like an electron, a particle like an electron, is moving, the less you know about its location, and vice versa. The more you know about the location of where an electron is, the less you know about how it is traveling. So you never really know exactly where and how an electron is traveling. The best that we could do is really come up with the idea of what is referred to as sort of a high probability of finding an electron in a certain location uh, in the atom. There is usually a very high probability of finding electrons near the nucleus because electrons are negatively charged, nucleus is positively charged. So there is an attraction between electrons and the nucleus. And there's usually a pretty good probability of finding electrons near the nucleus. As you move away from the nucleus and get farther away, the probability of finding electrons really does start to come down as a result of that. So this is really sort of the version of the model of the atom that we know. Um, Also in this version, the nucleus is really most of the mass of an atom. And that is because when we think about the three subatomic particles that make up an atom, which are protons, neutrons, and electrons, it is the neutrons that is the heaviest, followed very closely by protons. And the electrons are actually really light compared to the other two. It's about 1,800 times lighter than a proton or a neutron. So electrons are really light in terms of mass compared to the protons and neutrons. And that's why when we think about the atom, where we have the nucleus that has the protons and the neutrons, each of them are individually 1,800 times heavier than an electron. So it does make sense that most of the mass of the atom is the nucleus. We also got into some other sort of ideas, including the atomic number. The atomic number is the number of protons there are in an atom. Remember that the number of protons will also equal the number of electrons if the atom is neutral. So if it has no charge, then all the positive charge of the protons need to be balanced out by all the negative charge of the electrons. A reminder, as I mentioned last time, though, this is the definition of the atomic number. The atomic number is not the number of electrons. It is only the number of protons. You can find the atomic number there on the periodic table. Once again, it is the number typically above the symbol is the atomic number. That, along with the mass number that we talked about, which is the number of protons and the number of neutrons. Once again, as we talked about, the number here on the bottom is not the mass number. So the mass number is not found on the periodic table. It is only the atomic number. And you can use the mass number minus the atomic number, and that will give you the number of neutrons there are. So if you take the mass number minus the atomic number, give you the number of neutrons. We typically write these things with the symbol mass number up on top left, atomic number bottom left there. Any questions on any of that stuff there? Remember that when you do calculate protons, electrons, neutrons, mass number or atomic number, they all should be positive whole numbers. And that's a really good way to remember that the number on the bottom there, the periodic table, they are definitely not usually whole numbers. So it's definitely a good way to remember not to use those things. Any questions on any of those things? I think we might have talked about last time as well, you know, if something does get a charge, did we talk about that, right? If something had a charge, I think a little bit at the end there. If something did have a charge or does have a charge, those are what are referred to as ions. And those are things that have charges. And things with charges are usually either cations, which are positively charged, or anions, which are negatively charged. Cations are usually made by losing electrons, and anions are made by gaining electrons. And that really is what happens when something does gain a charge. So, you know, if we had something like phosphorus 30 here and 15, and this was a -3 charge. What we would look at here is, again, our atomic number, which would be 15. That gives us 15 protons. Our mass number, which is 30. 30 minus 15 would tell us we also actually have 15 neutrons in this example. But now when we look at electrons, it does have a charge. And that is the one thing that changes. In this case, we actually would have 18 electrons. And if you have 15 positive guys and 18 negative guys, that's going to leave you the -3 left over for the charge. And that is where the charge comes from. So when things do gain charges, it is just electrons to change. Why should we not ever change the protons? Yeah, because the protons out of all three of those particles, right, are the most important, because it is what tells you what element you're dealing with. If you look on the periodic table, there is never a atomic number that repeats. So every single element has its own unique atomic number, which means it has its own unique protons. So if you change the protons, you just change the element and it's no longer the same element. So this obviously would be an anion. And then, you know, if we had something like calcium here that had a +2 charge, once again, we would look at the atomic number here, which would be 20 protons. We would look at our mass number here, which would be 40 minus 20 gives us 20 neutrons. I'm like picking the whole numbers here. And in this particular case, it actually has a +2 charge. The positive tells us it's a cation. It also tells us basically it lost electrons. That's why it's positively charged. It's positively charged because, frankly, it has less electrons than protons, right? So it is more positive. And the 2 tells us how many. So really, if we just look at the atomic number, which is 20, and take away 2, that tells us it has 18 electrons in this case. That is 20 positives, 18 negatives, leaves you a +2 left over. And once again, that is where the charge comes from. Same idea with our negatively charged guys. It's negatively charged because they have more electrons than protons, so more negative charges than positive charges. Any questions on that there? All right. Isotopes, which is sort of what we were talking about here. Isotopes, again, are the same element, but they do have a different mass. And what makes them have a different mass is they have a different number of neutrons. One of the nice things about isotopes is, for the most part, protons and neutrons in a normal sort of chemical reaction, chemical process, they really don't participate. So it's really just electrons that participate in most cases. So a lot of times isotopes are, there's a number of isotopes of many elements that are radioactive. So one benefit of using isotopes, for example, in research is you can basically follow the radioactivity and you can follow where something goes. For example, I used to do work with radioactive copper, and radioactive copper, regular copper in the body basically does the same thing. So you can use some radioactive copper and you can follow through a pathway where all the copper basically ends up by following the radioactivity. It's a really nice thing. It will do the same chemistry in the body as regular copper. So that's one sort of benefit of isotopes and using sort of radioactive version of isotopes, is they actually will do pretty much the exact same thing in the body or anywhere else as the non-radioactive version. Any questions on protons, electrons, neutrons, any of those things? All right, so let's now actually talk about the number that we find on the bottom of the periodic table, not the very bottom of the periodic table, but on the bottom of the boxes. So once again, if we look in the box there, this number right here, which is not the mass number, this is really what is known as the atomic mass. And one of the fundamental properties of an atom is its mass, but they are extremely small, as we've been talking about. So you can't really pick one up and just kind of put it on a scale or anything like that. So oftentimes in chemistry and other places where we really can't sort of maybe directly measure something, what we like to do is sort of pick something to use as a standard and pick something as a standard to compare everybody else to. And for atomic masses, they picked an isotope of carbon, and it is the carbon-12 isotope, for which the standard was picked to be. And the carbon-12 isotope has a mass of exactly 12.00 AMU. AMU is atomic mass unit. It's a unit of obviously atomic mass. And to be frankly honest with you, probably outside of maybe this chapter, we'll never really use AMU in most calculations. But it is sort of a unit of atomic mass. We will use more convenient units later on, which are grams per mole, which is the molar mass. But you can basically take off the periodic table these values. So what they did was some experiments. And for example, they found that on average, a hydrogen atom is about 8.4% as big as the carbon-12 isotope. So they basically just did a quick little math move here. And that's basically 8.4% converted into a decimal, right? Move the decimal place 2 places to the left, and they are divided by 100, whichever way you like to do that. And we get a value of 1.008 AMU. And if you kind of look on the periodic table underneath hydrogen, that is pretty much the number that you will see depending on your periodic table and depending on how they may round. When we take that number for hydrogen, what that basically means is for hydrogen, there is 1.008 AMU in an atom is basically the units that you would sort of take. Typically, when we take atomic mass and later molar mass off the periodic table, for the most part, we take it to about 4 significant figures. So depending on your periodic table, there may be a bunch of numbers. or there may be less numbers, but usually the general rule is if you go to the periodic table and you kind of grab that number, 4 significant figures is usually what you kind of take it to use in a calculation. We obviously can find that on the periodic table, and again, it is the number that we see underneath the symbol. Now, if we chose the carbon, the carbon-12 is sort of the standard that they use to compare everybody else to. So they basically said the carbon-12 isotope has a mass of exactly 12. And they basically said, all right, so this guy here that's about this big is 12. This guy over here is only about 8% as big. So they do like a little calculation, go 8% of 12 is 1.008. So then the mass of hydrogen should be 1.008. So that's what that is for, yeah. Other questions on that? So since they did choose this carbon-12 isotope as a standard to compare everybody to, and it has a mass of exactly 12, when we actually do look on the periodic table, though, underneath carbon, it actually doesn't say 12. It does say 12.01 in most cases. And really the reason for that is what we see on the periodic table is actually the average atomic mass, even though nobody ever calls it average atomic mass, but they are actually the average atomic mass, and they're really the average atomic mass of all the naturally occurring isotopes for that element. So for example, something like carbon, there's a carbon-12 isotope, which is about 12, and there's a carbon-13 isotope that has a mass of about 13 and some change. So what we see there is actually an average value of those naturally occurring isotopes for that particular element. And that's why when we look at something like carbon, it has the different number than you might expect. How do we calculate the atomic mass? We do it like this. To calculate the atomic mass, like we kind of see on the periodic table, what we do is we take all the naturally occurring isotopes and we take the percentage at which they occur. So very commonly, for example, it is sometimes referred to as percent abundance or relative abundance, is really the percentage in nature of how much this isotope appears versus the other one. So for example, you could have an isotope of one element that appears about 90% of the time, and the second isotope appears about 10% of the time. And that's what we're talking about when we talk about percent abundance and stuff like that. If you gather up all the naturally occurring isotopes together for a particular element, all the percentages should add up to approximately 100, right? So they all should add up to approximately 100%. So what we do is we take the percent abundance of the first isotope and we multiply it by the atomic mass of the first isotope. Then what we do is what a lot of people mess up on, we actually are going to add, not multiply or anything like that. We're going to add that to the percent abundance of the second isotope times the atomic mass of the second isotope. And if we should happen to have 3 isotopes, we would just continue that pattern. So we just kind of continue that pattern. If we had 3, 4 isotopes that are naturally occurring, you keep taking the percentage times the atomic mass added to the next percentage times the atomic mass. And when you add all those numbers together, you will get what you kind of see on the periodic table, the average atomic mass for each of those elements. When we use a percentage in a calculation, should we leave it as a percentage? We should convert it into a decimal. So to convert a percentage into a decimal, once again, you can do one of 2 things. You could either move the decimal place 2 places to the left, or you could divide by 100%, right? And that will move the decimal for you 2 places to the left. So whichever way you want to do it. So let's take a look at, this is carbon, and we have our 2 isotopes of carbon. This is the carbon-12 isotope, and this is the carbon-13 isotope. And what we see is, for the most part, the carbon-12 isotope occurs about 99% of the time, and the carbon-13 isotope occurs about 1.1% of the time. The carbon-12 isotope has a mass of 12, and the carbon-13 isotope has a mass of 13.003. The first thing you would want to do in a problem like this is, like I said, take a second and just take a look at the percentages and make sure that it adds up to 100%, right? So it might not be perfectly 100%, might be a little bit over 100, might be just a little less than 100, but it should be in that 100%. If you add up the percentages and it's not 100%, you are missing an isotope somewhere. Yeah, so somewhere there's probably some information about how you can figure out what's missing or something like that. In this case, if we quickly sort of add it together, you got basically 99 and 1, which is about 100. So we got about 100% going on here. So if we were to calculate the atomic mass here of this carbon isotope, we will take the first isotope. So we'll do the carbon-12. We will take the percentage. I'm going to move the decimal place 2 places to the left, which will give me 0.98897. We're going to times it by 12 AMU. That is my first isotope. I'm then going to add it to my second isotope, which is here. So once again, if you do not want to move the decimal, you could do this 1.11% divided by 100%. And that will move the decimal for you. So whichever way you like to do it, you can do it. We then would times it by the mass of the second isotope, which is 13.003 AMU. And again, this is our second isotope. And if we do all that good stuff there, we should get that number in the box, I would hope. Actually, I get 1202 on my calculator personally, but you had like 12.02 AMU maybe, which would be the atomic mass there of our carbon atom. They might have rounded a little bit the first number, the second number to get it to that, but somewhere in that ballpark. Any questions on that there? So this is the way that we calculate the atomic mass of a element. We take all the naturally occurring isotopes and basically follow this formula, and we should get pretty close to the number, again with rounding and stuff like that, pretty close to the number that you would see on the periodic table underneath that element. Any questions on that there? Yeah. And then added it to this second two, yeah. Yeah, so you would multiply these two, get a number if you like, multiply these two, get a number, and then add these together, that or that, I guess, depending on where you're at. Other questions? All right, so why don't you try one here? Bromine has 2 stable isotopes, bromine 79, which is 50.70% abundant, and bromine 81, which is 49.32% abundant. The atomic masses of each of those isotopes are 78.92 and 80.92. Determine the average atomic mass of bromine. So take a moment or two and see what you come up with. Okay, let's take a look. So once again, we have our percentages here, both isotopes. And quickly looking at it, we got one that's about 51. We got one that's about 49. So that's about 100. So we're good. We have all of our isotopes that we need. So we're going to follow our formula there, which is we're going to take the atomic mass, and that would be our first isotope, which is this guy. Once again, here, I'm just going to move the decimal point 2 places to the left, which will then convert my percentage into a decimal. And I'm going to multiply it by the atomic mass of that first isotope, which is 78.92 AMU. I am then going to add it, and I'll just go underneath here. I'm going to convert this guy once again into a decimal by moving it 2 places to the left, gives me 0.4932 times the atomic mass of my second isotope there, which is our 80.92 AMU. And looks like here 79.92 AMU is what we're looking at. So it looks like maybe D would be the right one there. Any questions on that there? Again, if you look at the periodic table under bromine, it's about 7990. So again, with rounding and stuff like that is pretty much how we get to those numbers that we see on the periodic table. Any question on atomic mass here? So once again, as you can see, atomic mass is different than mass number. So mass number, protons, neutrons, atomic mass here, again, sort of the mass of the entire isotope or element. Any questions on that? Okay, then let's talk about the periodic table here officially. That's the periodic table. Good talk. So the periodic table, again, there's a couple of things. First off, a column on the periodic table, which is going up and down, I guess. That is what is referred to as groups. If you're old like me, family. Not too many people call it families anymore. Most people call them groups these days. As we've talked about, there are different sort of numbering that you commonly will see on the periodic table. In most chemistry class, including this class, we do use the sort of A numbering, if you will, which is sometimes referred to as the representative numbering. And with the A numbering, this is group 1 right here. That is group 2. Skipping everybody there, that is group 3. That is group 4. That is group 5, group 6, group 7, and group 8. So those are numbering. Most people don't call it like 1A, 2A. Most people just call it group 1, group 2, and so forth. But that is groups, again, going up and down across the periodic table. A period, on the other hand, is going left to right on the periodic table. And there's usually 7 periods. There's period 1, period 2, period 3, period 4, period 5, period 6, period 7. Again, heading in this direction here. As we've talked about a number of times up to this point, again, the number above the symbol, that is our atomic number, which again is our number of protons that there are. So it's really important to understand which way groups go, which way periods go. We've talked about it, but just to remind everybody, on most periodic tables, you will find hydrogen right above lithium. And group 1 actually starts with lithium, not hydrogen. So although hydrogen is hanging out there on group 1, it is not a member of group 1. It's really just there for a specific reason. Hydrogen has some unusual properties, which are similar to what you see in group 1. But it actually does not belong to group 1, even though on every single periodic table, it's sitting right there on top of lithium. Elements on the periodic table are divided into sort of 3 categories. They are metals, non-metals, and metalloids. And metalloids are sometimes called semi-metals. Pretty much on every periodic table, you can find this sort of staircase kind of highlighted coming down from right where boron is at the very top corner there. And this guy right here is boron. So usually from boron coming down kind of in a stepwise fashion here. There's usually what is referred to as the staircase. To the left of that staircase are metals, including the 2 rows that are at the very bottom. Those are metals as well. Metals are really good conductors of heat and electricity. They can be hammered into thin sheets, pulled into wires. They typically are very shiny. For the most part, all metals are solids at room temperature. The one exception is mercury, which is Hg. And on most periodic tables, Hg is sometimes a different color. The lettering is sometimes blue or something like that to sort of stand it out. But mercury is actually a liquid under room temperature. Up to the right of that staircase are nonmetals, and nonmetals pretty much have the opposite characteristics of metals. They're dull, they're brittle, they're insulators, they're not so great conductors of electricity. Also, nonmetals have a much different variety of states. So a lot of them are solids, a lot of them are liquids, and some of them are gases as well. In addition, a lot of the nonmetals that we have are those diatomic elements like hydrogen, nitrogen, fluorine, chlorine, bromine, iodine, oxygen. So a lot of these guys, all these guys here are actually nonmetals, and they're the guys that come as diatomic molecules, as elements. The reason for why hydrogen is not part of group 1 is hydrogen is right there, and it is color coded once again as a non-metal. So even though it is hanging out over there with all the metals, hydrogen is actually a non-metal. And again, that is why it is not part of group 1. I probably said this before, but years ago, they would also a lot of times put like hydrogen over here as well on periodic tables. They really don't do that anymore, but hydrogen is a non-metal. And again, that is really why it is not part of group 1, which are all metals below it, where lithium is and all those kind of guys. Now, if we look at the staircase there, these are metalloids, are semi-metals. Depending on your book, some people throw boron in there. I can't remember if yours does or not, but some people include boron or not. But again, this staircase sort of comes down here like a stair. And these are our semi-metals or metalloids. And basically, these elements have characteristics, the same element that would be, some characteristics are very much like what we see with metals. And the same element will also have some characteristics that are very similar to what you see with non-metals. So there's sometimes like semiconductors and stuff like that in that sort of range. And it makes sense based on where they're at. You're basically coming from metals and then into non-metals. So these guys right here really fall on kind of both sides of the staircase there in terms of their characteristics. They can be very metal-like and also be very non-metal-like as well. Now, some of the groups do have special names that you do need to know of, and we went over some of these, I think, during discussion, but just to make sure officially here, group 1, which again starts with lithium, those are what are referred to as the alkali metals. So as we see here, right there and down is group 1. Group 2, which is right next door, are the alkaline earth metals. That's your beryllium, your magnesium, and all those good guys there. Group 7, which is over here, these are the halogens. And right next door is group 8, which is the noble gases. So those are the noble gases. Noble gases are chemically inert. They are super stable. And as we'll talk about when we talk about bonding, pretty much the whole purpose of bonding, no matter what type of bonding is happening, is for everybody to end up with the same electron configuration as noble gases, because they are super stable. So really the whole basis of bonding is for everybody to basically become like a noble gas. They don't become the noble gas, but they become like the noble gas with the number of electrons that they end up with, and that makes them very stable in a sort of a bonding situation. Yes. It does. It depends. So I'll be honest with you, it depends. Is there one? Is there like right there? Yeah. So you could see on maybe this periodic table, there's a lot of weird symbols like in this area, right? And depending on when your periodic table was kind of made and printed, that's usually where they stick like, we haven't decided if we're going to call that an element or not, like a new element. So that's where they kind of stick those type of things. They give us sort of temporary weird symbols, like a lot of these like U, and all these kind of weird ones. So you will see some variations on periodic tables. You'll see like some like here where there's nothing there. And you'll see some where maybe it's filled in. And, depending on when it was printed, maybe your periodic table will lay up right about there and stuff like that. So there's some variations there. The good news is we really don't deal too much with any of those guys in that region. These are all where people kind of make elements in the laboratory, basically, and stuff like that. And that's where they kind of stick them. For the most part, radon down there is the end of the noble gases. Yeah, for the most part, yeah. Other questions? As I mentioned before, there's also 2 rows set to the bottom of the periodic table, and this is the lanthanides and actinides, because that those are the two elements that they really should follow, which are right here. And if you look at the numbering, it goes like 56, 57, 72. It goes 56, 57, there's 58. So that row actually goes right there. If you follow the numbering below it, it goes like 89, 104, 90 is right there. This one goes here. So technically speaking, these two guys go right into this spot on the periodic table. I've never seen anybody really put it in a book in the right spot, because obviously your periodic table will now be super wide and won't fit in your cover and stuff like that. So they're usually set to the bottom. We don't deal too much with those in here. A lot of radioactive elements are found down there. A lot of, when we speak about man-made sort of elements, you know, are sort of found down there. But we don't really deal too much with those guys. Yeah, so I think this is your question. So we'll go like 57, which is lanthanide, yeah. And then there's like 72 right next to it. Technically, right here, that row would go like right there, and then right between those two. It does. So that's where these guys come in. They actually come in way over here, like on this, you know, kind of the after those guys, they would kind of come in. Yeah. Other questions on that? Okay. Now, between group 2 and group 3 on the periodic table, pretty much here, big green box. I'll exit out like a bad answer on Family Feud. So right there in that box there, those are the transition metals. And transition metals, as we'll talk about with naming, one of the characteristics of transition metals are they pretty much can make multiple types of charges. So they have variable charges. They don't really a lot of times have fixed charges. There's only 3 that really do have fixed charges in the transition metal region. And that is these 3 right here. That is the zinc, the cadmium, and the silver. These guys here actually have fixed charges. Everybody else in the transition metal region can make a variety of charges that will occur. That's also why these 2 sort of rows on the bottom, which technically go right in there, are also sometimes referred to as inner transition metals, because they technically kind of go in the middle there between where the transition metals are. Any questions on any of that there? So obviously you do need to know the periodic table, the names of the groups, which way groups go, which way periods go, where metals, non-metals, and metalloids are, and some characteristics, obviously, of those things. Any questions on that there? All right, we're going to then talk about really electrons and electron configuration and sort of where electrons are in the atom officially here. A lot of what we kind of see happen with electrons and what happens in a normal situation with electrons are this. Electrons are found on different energy levels. And you could do something to electrons to excite them. For example, you know, if you ever done a flame test and you put the element in a flame, that's going to add a lot of energy. And what happens is the electrons in that atom are going to be excited, and they're going to go to a higher state of energy. Everything in chemistry and everything in life, people like to be at a lower state of energy. So what's going to happen eventually is that electron will want to work its way back down. The result of that is the idea of the conservation of energy, which basically says we don't lose or create energy or anything like that. So the energy has to be given off from the atom as the electron is transitioning down. And depending on where that energy comes off of, it will come off as a wavelength, or a wave, I guess is a better way to put that. Sometimes referred to as a photon of light. And that wave will have a specific wavelength which may correspond to the visible part of the spectrum, for example. And that is where we see colors, like red, orange, yellow, green, blue, indigo, violet, Roy G. Biv, yeah. It may not fall into the visible part of the spectrum. It may fall into the ultraviolet part of the spectrum, the infrared part of the spectrum, and so forth. But if it does fall in that sort of visible part of the spectrum, we will see color. You maybe have done this if you boiled water to make pasta or something like that, and maybe it overboils. And if your stovetop, there is a flame stovetop, the water kind of hits the flame changes color real quick. It's like a yellowish type color and goes away. That's really the sodium ion saying, thank you very much for exciting me. And the sodium ions just got all their electrons excited. And that's why it turned that kind of really bright yellow color for a second until it all the electrons relax back down. So if you ever done a flame test or fireworks on the 4th of July, right? When you shoot off the fireworks, legally, right? You have they explode, which obviously provides a lot of energy. And depending on what elements there are in those fireworks, all the electrons in those elements will get excited. They'll come back down, and you go, "Oh, pretty colors," as you're watching it again in a legal show and all that kind of stuff. Now, there are different parts of the electromagnetic spectrum, and the relationship between a wave length and energy is this: the shorter the wavelength, the higher the energy. So the shorter the wavelength, it typically will have a higher frequency, which means it will occur a lot faster, and that's usually associated with something with a higher energy, and vice versa. The longer wavelength usually is associated with a lower energy. Longer wavelength has a lower frequency, is kind of moving really slow, and it's kind of big and moving like that. It has a lower energy. So this is electromagnetic spectrum. On this side over here, that is like 10 to the 5th wavelength. Over here is a lot smaller, 10 to the minus 11. It's much smaller on this side, which means this is much higher in energy. On this side is a longer wavelength, and it is a lower energy. So on the longer wavelength, lower energy, we see things like radio waves, right? So we listen to the radio, we dial our radio to a specific frequency, like 95.5 megahertz is basically the frequency that you're dialing into your radio. That has a certain amount of energy. Next, in terms of energy, is microwaves. So microwaves have enough energy to spin water molecules really fast, right? And get like a pizza in 3 minutes. It's the magic of science, right? So we get those things going on. We get to the infrared. That is typically where we feel heat and that type of feeling. We then get to the visible part of the spectrum here. As I mentioned before, that's where we see colors. And even with colors, there's a difference in terms of energy. Red is actually longer wavelength, so it's actually lower in energy than the purple side, which is a shorter wavelength, and or violet, whatever you want to call it, on that side, and that has a much higher energy. So even within colors, there's a separation in terms of energy associated with the colors that you see. Then after the visible part of the spectrum, we have the ultraviolet part of the spectrum. That is where we wear sunblock, yes, so we don't get so burnt when we go outside, right? Because it's kind of high energy. So we put on some sunblock. Then we have x-rays. That is why, they give you a lead vest, and usually they leave the room when they shoot your x-ray, right? Because it's kind of high in energy and stuff like that. And then we have gamma rays at the very end, very short wavelength, very high energy. It's really just kind of pure energy. It's a radioactive sort of particle in a sense. It's very high in energy. So as electrons are sort of transitioning from one energy level to the next, they will give off that energy in the form of a wave, photon of light. And again, it could fall really anywhere in this sort of spectrum. And we may see colors. Like I said, if it's in the visible part, you may feel something else depending if it's in a different part of the spectrum. There's a same sort of picture there. All right, identify the form of electromagnetic radiation, each of the pair that has the greater energy. Yellow light or blue light. Yellow actually would be less energy than blue. Again, this part of the visible part of the spectrum is shorter wavelength, higher energy. Longer wavelength, lower energy on that side there. Ultraviolet or infrared. UV actually has more energy associated with it. X-rays or microwaves, well, we don't really leave the room too much when we're microwaving. So I'm going to go with X-rays as the higher energy in that particular case. Any questions on those there? Now, we do see a spectrum sometimes when we look at elements, and one thing that elements do that is a little bit different than other things like the sun, for example, is they have what is referred to as sort of quantized energy. And what that basically means is when we are talking about electrons transitioning from one energy level to the next, they will always gain and also lose energy, enough energy pretty much to make the entire transition. So they will never find themselves between energy levels and go, I'm kind of tired, I just want to lay it up here. So they will either gain enough energy to kind of get to this energy level, or they'll lose enough energy to drop back down to the next energy level, but they'll never sort of, stop in between. Quantized energy, a very easy sort of example of it is like when you walk stairs. Yes. When you walk stairs, you either find yourself on this step, usually, right? This step or that step. Like I was saying, you don't usually find yourself halfway up this step and say, I'm just going to rest here for a bit. Yeah. And fall over. So you either have enough energy to make it to this step, or that step, going up and also going down. Going down, you have enough energy to make it from that step to that step to that step. Now, there's also people, right, that go right by you on the side that decide I like to do 2 steps at a time. Yes, right? They have enough energy to do 2 steps at a time, 3 steps maybe, not usually more than 3, I don't think. But electrons are the same thing. There are some electrons that could gain enough energy to go from like 1 energy level up to like 2 or 3 energy levels and lay it up there, or come back down 2 energy levels or 3 energy levels and stuff like that. So that's the idea of quantized energy. And because electrons travel that way, they give off a very specific spectrum, which is referred to as a line spectrum. And a line spectrum is pretty much what it sounds like. Every single element will give off distinct lines of color at specific wavelengths. And they're so distinct that every single element will give their own unique spectrum that you could actually look at it and go, oh, I see a red line at this wavelength and a blue line at this wavelength and a green line over here at this wavelength. Oh, that's this element, because that's the only element that will have those lines at those specific wavelengths. So you could actually identify a particular element based on the lines that you actually see come up in those type of spectrum. And that's very different than what happens with something like the sun. The sun has what is referred to as a continuous spectrum. It gives off pretty much energy all across the board. You see everything happening at once. So something like the sun, you could think of as a continuous spectrum. And we equate it to a set of stairs, like you walk up a ramp, right? And when you walk up a ramp, you literally can stop anywhere you like along the way, right? You're not going to run into any trouble. And that's sort of what a continuous spectrum is. Everything just comes out at once. The sun is like that. But elements, when they're heated or excited, their electrons, again, do the quantized, more stair type approach. And it gives off this different spectrum. A continuous spectrum would look more like rainbowy if you kind of put it in a prism, like everything would just kind of rainbow out. You wouldn't see these distinct lines that would happen. So what are these energy levels? The energy levels, when we talk about where electrons are referred to as principal quantum number. And that is N, which is, again, a fancy way of saying basically the energy level. And that N is basically our energy level. An N that is equal to 1 is a ground state, and that is the lowest in energy. And I would also put it closest to the nucleus. Anything that is basically N2 through 7, those are what are referred to as excited states. Those are obviously then going to be higher in energy. And you do get sort of further away from the nucleus as you continue up that scale towards 7. So on these different energy levels, we do find electrons, and they can be housed in certain sort of theoretical places within the atom. And those are what I refer to as orbitals. And on different energy level, there's different orbitals. And here's, I was talking about sort of the quantized idea of energy. These are different energy levels. On the very first energy level, there is only a 1s orbital. There's only really one place for electrons to be found, and that is in an s orbital. And when you get to the second energy level, for example, you also have an s orbital, and that is where you start to see p orbitals basically start to occur. And as you continue up, you get more and more orbitals. These orbitals are really things that have shapes, but they're really probability maps. As we're talking about, there's really no good way to know how an electron is moving. There's just these sort of orbitals, which are maps of places within the atom where you have a very good probability of perhaps finding an electron. Now, as electrons really transition from one energy level to the next, they either got to absorb energy to do that or release energy. And as electrons go from a lower energy level to a higher energy level, they actually need to absorb energy to do that, right? The atom's got to absorb energy. So like my example earlier, where, you know, you did put the flame in there and it heats it up, or like fireworks where it explodes and provides all that energy. So in order for this electron to work its way up, it has to absorb energy, the atom. The opposite is true if our electron is starting at a higher energy level and needs to work its way down. It needs to actually release energy or emit energy, basically. It has to give off the energy from the atom to allow that electron basically to come back down. Any questions on that there? All right, so I think we will lay it up there for today.